Hello everyone, this is Mr.DHAKSHUNHAAMOORTHY, Assistant Professor, AIML Department. I am handling subject 22 CS 302, Computer Organization and Architecture, Unit 1, Computer Fundamentals, topic, Basic Operational Concepts. This one is basic architecture of computer. It consists of ALU, arithmetic logic unit, program counter, instruction register. For accessing memory, we are using memory data register, memory address register, through which we are accessing the memory. Mainly we are using control unit, which controls all the activities of processor. We are using general purpose registers R0 to Rn. This memory, we can access data in bidirectional, whereas address is unidirectional. The control the processing unit provides address to the memory. Register and its types. Here, accumulator is the main primary register through which we are passing first data, and the second operand, which is sent to the ALU by using registers, general purpose registers, and DR is data registers, AR is address registers, PC is program counter, MDR is memory data registers, MAR is memory address register, IR is index register. Basic operational concepts. Program consists of a list of instructions is stored in the memory. Individual instructions are brought from the memory into the processor, which executes the specified operations. Data to be stored are also stored in the memory. The execution of the program starts when the PC is set to point to the first instruction of the program. The contents of the PC are transferred to the MAR, and a read control signal is sent to the memory. The addressed word is read out of the memory and loaded into the MDR. Next, the content of the MDR are transferred to the IR. At this point, the instruction is ready to be decoded and executed. If the instruction involves an operation to be performed by the ALU, it is necessary to obtain the required operands. If an operand resides in the memory, it has to be fetched by the sending its address to the MAR and initiating a read cycle. When the operand has been read from the memory into MDR, it is transferred from the MDR to ALU. After one or more operands are fetched in this way, the ALU can perform desired operation. If the result of the operation is to be stored in the memory, then the result is sent to the MDR. The address of the location where the result is to be stored is sent to the MAR, and a write cycle is initiated. At same point, during the execution of the current instruction, the contents of the PC are incremented so that the PC points to the next instruction to be executed. Thus, as soon as the execution of the current instruction is completed, a new instruction fetch may be started. Memory organization, viewed as a large single dimensional array with an address. A memory address is an index into the array. Byte addressing means the successive address one byte apart. But most data items use larger words. For MIPS, a word is 32 bits or 4 bytes. Then the consecutive memory addresses 0, 4, 8 and 12. Here registers holds 32 bits of data. For the byte addressing 2 power 32 bytes with the byte address from 0 to 2 power 32 minus 1. Whereas 2 power 30 words with the byte addresses 0, 4, 8, 12, 16 plus 2 power 32 minus 4. Memory layout. Here in this slide we can able to see the memory records width from 0 to 31, that means 4 byte instruction, and memory addresses 0, 4, 8, 12, 16 and so on. What are the least two significant bits of the word address? Here least significant bit means the memory record for which we are taking the data from 0 to 7 is the least significant byte. Least significant bit means 0th bit we are considering as least significant bits. Similarly, most significant bit is 31st bit of the particular record is most significant bit. Here we have to measure the performance of the particular processor based on the execution time. When execution time is more, then performance is very low. That means performance is inversely proportional to the execution time. The CPU execution time equal to number of instructions in a program and clock cycle per instruction divided by clock rate. Here, try to achieve CPI, clock cycle per instruction, equal to 1 with a clock that is as high as that for CPI greater than 1 designs. Is CPI less than 1 is CPI less than 1 feasible? Here, define an instruction set. Make it simple enough to require a small number of cycles and allow high clock rate, but not so simple that we need many instructions even for very simple tasks. Design a hardware for CPI equal to 1. Seek improvements with CPI greater than 1. Design ALU for arithmetic and logic operations. Design memory and I/O structures to support ultra high speed CPUs. In the example, we can able to see assembly line analogy. Here single cycle CPI equal to 1, the items take longest to inspect dictate the speed of the assembly line. When we are doing parallelly two different operations simultaneously, then CPI greater than 1, then it is faster than the single line